Before I actually show you MVT and rolls, if this is a function, and it is a function, do we all agree it's a function? Oh, I do agree. Yeah, thank you, Meg. All right. Function, yes? Yes. Yeah, that's a function. I'm going to redo MVT and rolls with you quickly. Yeah.
I feel like I didn't understand it whenever it was like infinity to negative infinity, but whenever it's given the boundaries, and you just do the sign chart, plug the boundaries into the derivative.
Okay. Didn't I teach y'all extreme value theory? There's really not more to that. Listen, here is the extreme value theorem in a nutshell. Okay, well, I think we're confused about what local and absolute means. So let's talk about that for just a second.
I understand that. I just don't know when to use it. Just like on some of them, use extreme value theorem, use it.
A local max, that would be a one on the left.
Okay, listen, it's like use extreme value theorem, use this. But whenever we did one, and we asked, we were like, there is no extreme value theorem. But then the solution for it, even though it wasn't extreme value theorem, still found the maximum in the middle. So like, why are we doing
Maxes and mins are extreme values. So if your function, okay.
Like one of them wasn't continuous, but still.
There's a local max and a local absolute.
Are you talking about number 8?
I don't know.
So just and I'll do a couple from your homework. I'm trying to think of what Lord, I can't even remember where we ended. Number 10.
Whatever that first was.
Okay, so the directions on this say identify each x value at which any absolute extreme values occur. So absolute meaning the highest or the lowest. So if you're looking at something like this, this would be absolute, this would be local or relative, same thing, right? Because it never goes above this, it's the highest point on the graph. This is a high point, meaning the direction changes, and that's kind of what we were doing with MVT theorem. So here the function is increasing, right? It's going up, going up, going up, going up. At this point, it stops going up, it changes direction, and it starts decreasing. Okay? So this is where the derivative is positive. This is where the derivative, and this is getting into MVT some, but this is where the derivative is negative. So yes, what you'll do is the whole goal here in both of these, right, is we're finding every place that the derivative is 0. Okay, because that's the place where it could possibly change direction. Now maybe it doesn't. Maybe it's what we call that stationary point where it just stops and rests. Okay, so
Go to positive once it starts going up.
right. So stationary just means that the derivative is 0, and it could mean, think about that particle. Remember we said the velocity could be 0, but it doesn't mean that it necessarily changes direction at that point. It could just stop and rest a second and then keep So on this graph, the derivative here, all right, so I put these same points. I don't know what these values are, but they correspond to these mins and maxes, right? So here the derivative would be positive because I'm increasing. So if I didn't have the graph to look at, if I just had an equation, I would be plugging in where it's 0. So here it's negative, which means my graph is decreasing. Here it's, again, positive, so it's increasing. And here, negative, so it's decreasing. Okay. Now, for the ones we did for MVT, they had endpoints on them, right? They were cut off. They were between this value and this value, which means there's a point here, a starting point, and an ending point. They didn't do this, they did this, right? Instead of arrows, it was points. It was just a piece of a graph. It didn't go on forever. So what we had to do was we had to find out, well, I know that this is a maximum because it literally changes direction. It stops increasing, it starts decreasing. I know that this is a minimum, a maximum. This should be a min because it goes down, and this should be some type of minimum because it goes down. The problem is, are they relative or absolute? Or local or absolute? So the only way to find that, if I'm not looking at the graph, is to plug these values in to f of x and see which one's bigger and which one's smaller. That's why we're plugging them in.
Which value you get out is bigger.
Right. So let's say this was 0, 1, 2, 3, and 4. Yes, you do. Then I would say, okay, what's f of 0? I'd get some value there. Okay, what's f of 1? I'd get some value there. And so what I'm going to do is I'm going to compare the maximums. Whichever one gives you the biggest maximum is your absolute maximum. Whichever one gives you the smallest minimum is your absolute minimum. Does that make sense?
What if you aren't given the boundaries? Like, what if it's just negative and
Okay, so I have to look if it's going down forever or if it's not. So if I just have, you're saying
like depending on the function?
if there's no endpoints, right? If I have, let's say I have 2 zeros here. Let's say I'm positive, positive, negative. Is that what you mean? So I'm increasing, increasing, and then I start decreasing. The only thing I can really say here is that that's a maximum. I don't know if it's relative or absolute at this point since it's going on forever because I don't know where this started. Or you see, like I don't.
Yeah, they were like a heaviness on it. Wait.
Actually, I do know. Let's graph it. Let's think about it. If it's increasing, 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 always increasing, then it starts to, it's got to be absolute. Yeah, it's an absolute. This is where the derivative equals 0. So if this were the graph, if you had f of x equals x to the third plus, I don't know, 2x. You do the derivative, set it equal to 0, subtract 2, divide by 3 and square root. Those are negative. That's a horrible. Make it minus. So on my number line that I'm testing, I would have negative square root of 2/3. Square root of 2/3. Right. So for this one, I don't know. What do you get? If you plug into the derivative here, you put in a negative number, let's say negative 5. This should be positive, so it should be increasing. Here, if I put in 0, it's negative, so it's decreasing. And here, again, positive. So maybe I say, okay, my function is f of x is, and maybe, is this where y'all got confused? It's increasing on negative infinity to negative square root of 2/3. Are those the intervals y'all were getting confused on?
I was getting confused on where they got the intervals from, and like how they knew what was like working. and that's not necessarily what they were, but like how did they know that that's what? Yeah. Like
Algebraically.
you like plug in a number and you got this. How do they know that that number was local or absolute, stuff like that?
I got you. Which came in MVT, not extreme value. Did it come in extreme value?
For me, it was
It did. Okay. Okay. Give me some of the ones from extreme. Oh, you would need to. Let me finish this because I don't want to. These happen frequently on FRQ, and you have to justify when asked. It's not enough just to say where it's increasing. You have to say why. So you have to say because the derivative is. You can even say greater than 0 on these intervals. If the derivative is less than 0, it's decreasing. Yes. Remember, derivative is just slope of the tan line. We're doing the same thing over and over and over. We are just saying it different ways. You're exactly right. If you go back, so remember which one you're looking at. The bottom tells us the derivative. So we go back to the derivative equation, and I just plug in some value over here. I picked maybe -5 is what I picked. If I square -5, I get positive 25. It's going to give me 75. If I subtract 2, I'm still going to be positive. What do you mean undefined?
Like it was undefined.
Yes. Huh? What's undefined at 17?
So it's the derivative is x to the -3.
Right.
So you have x as a denominator. So when
it just can't be 0.
like,
So let me look at it. Let me write it.
like we're trying to set it equal to 0.
All right, so derivative. Okay, so I should have mentioned this, and I know what you're talking about now. Undefined points also make extreme values on the original function. So count those on your number line if you get an undefined. In other words, here, if I've got 2/5 x to the -3/5. You're right whenever I set this equal to 0. Because that 0 is in the bottom, it would be undefined. It's still a critical point to test that. So when I set this up, I need to have 0 here because I'm testing the points to the left and the right, seeing what happens there. Because even although it's undefined on the derivative, that does not mean it's undefined on the function. Because it could be, what if your function does something like this, right? So it just could be that it's undefined on the derivative and not the function. So always test your undefined points as well. And so if I tested this, well, whenever it's negative, what's my sign going to be? Negative? I got an odd exponent here on an odd root. So odds keep the same sign that they start with, right? Odd roots, whatever they may be, whatever sign is under here is the sign that ends up here. So if this is negative, then it's going to be negative here. If this is positive, then it's going to be positive, right? They keep the same sign. So if I plug a negative, I get a negative. If I plug a positive, I get a positive. So this is what my function is looking like. And for this one, it says between -3 and 1. So I have endpoints. I know this is a minimum value because my function changes signs from negative to positive at that point. But the question is it the lowest point on the graph, or is there a point lower?
Undefined points may be.
Yes.
What is it?
Critical points or extreme values. Right. So how can I tell without actually graphing this, if I don't have a calculator and I don't have anything else, how can I tell, is it a maximum, is it a minimum, what's happening, what's it doing? I'm going to plug in all of these critical values. First thing I'm going to do is -3. So that's -3 raised to the 2/5. It defined it in the problem. It said between -3 and 1. F of 0 is, of course, 0. And f of 1 would be 3 to the 2/5. So I need to know which is bigger, which is smaller. That's what I had. Where are y'all talking about? No, I'm just kidding. Sorry. So when you square a negative, I'm going to become positive, right? So this is really the 5th root of 9. So let's order these from biggest to smallest. Obviously, 0 is the smallest. Do you agree? Because these are both positive and positive. So that means since this is the smallest one anywhere on the graph, what is that point? An absolute minimum. Do you see how we figured that out? It has the smallest value. So, no, man, it's not a guess. It's not a guess.
No, it's estimation.
I thought there's sign beside the,
It's elimination process.
you're not in the red, it's square.
Yes, but I squared because, okay, so in this one, it was odd top and bottom when I took the derivative, but up top, this is always going to shoot me back out a positive number because I'm squaring it and doing the 5th root. That top number's even. It's going to cause me always to be positive. How what? Okay, so you don't, so it means something times itself 5 times gives you that value. So my question would be, which one's bigger, 1 or the 5th root of 9? I'm going 1. I think that's a... What is, somebody with a calculator tell me what the 5th root of 9 is. I'm sure it's a decimal. So hit 5, math 5, or either math 4, I can't remember.
It's like 1.5.
Is it? It's 1.5? I was wrong.
Well, we would have gotten that at barbecue.
But all I really need to know is this one is bigger than this one. That's what I'm looking for. Is Greg calculator or non-calculator? I never remember. Are y'all sure?
I'll write it down. Do you have a marker, Mr. Keith, so I can write it on the board?
Look at my desk drawer.
I feel like you should just memorize all your shit.
Out the 3 decimal places. All right. Does that clear that up a little bit? Do you understand what it is we're doing? Because this is basically the thought process for this entire chapter.
I didn't even know this. I didn't even know that it was.
Then I failed you on Wednesday and Thursday and Friday if you did not realize this.
Okay, so Gray is calculator, right?
Yes. It is. And it ties back into particle motion, or it will too, because we've already, that's what we were doing with particle motion, but we were calling it, instead of calling it the first derivative, we were calling it velocity, even though we were finding it. Are y'all okay?
We're better than we were. Right?
Let's take 2, and then we'll come back to get. Do y'all need me to do another one from EVT?
Yeah, I wanted to do EVT. Wait, that wasn't EVT. That was EVT.
5 math 5.
That was EVT. Was that the extreme value theorem or the?
You need more time for your homework? Okay. Are you talking about the graphs? You're talking about EVT or MVT?
Which was this? EVT or
This one?
MVT? What did we do?
All right, the next one. Yes, I'm gonna flip to the next. Yeah. Exception was that you understood extreme value theorem, because if you understand extreme value theorem, then mean value theorem is a piece of cake, and if you understand mean value theorem, then Rolle's is a piece of cake. But if you don't understand extreme value theorem, then you're kind of set up for failure to start with. So I apologize for that, because I did not realize y'all did not understand extreme value theorem. But now that you understand what it is that is going on here, are we all clear on how we find these extreme values?
If the value is less than 0, it's negative. If it's more than 0,
The
it's
what? It wasn't very calculus-y, but yes. So if the derivative is positive, the function is increasing. And I think that's what you were trying to say, man. And if the derivative is negative, the function is decreasing. And that's where we find these extreme values, is when we change from increasing to decreasing or decreasing to increasing. Does that make sense? Does it make dollars?
I feel like we've done something like this before.
Nobody. Thank you, Lizzie. Thank you. Nobody else was even paying attention to that. And if they were, they just ignored me because
What does it make dollars right here?
Did you get it?
Mine's good.
Okay. So, no, we're going to fix everything we got. We'll start the new stuff
I
tomorrow.
already did on my number.
We know, okay, so pulling in from extreme value theorem and everything else, we know that if the derivative is greater than 0, we're getting there, yes. Yes. Well, it's what you know, yeah. Call it what you can. They all kind of go hand in hand, in my opinion. Okay. Does that make sense? On the interval that the derivative is greater than 0, then it's also, so I'm going to add that if the derivative is positive on the interval AB, then it increases on AB. And just because you will see this, it's inclusive on the function, it's exclusive on the derivative.
Inclusive on the function.
Inclusive, yes, exclusive on the derivative. This is where you get into that little nitpicky stuff. It's not, it's general idea, remember, when we're switching
So
signs,
that means like that's the continuous and all that kind of stuff. Like the notes reflect that.
Okay, say it again.
It has something to do with like it's continuous on the interval.
Correct. Right. Right.
But it's differential on the exclusive.
Right.
Closed interval.
Right. Right. All these definitions start intertwining and coming back together. All right, so then with the same thing, if the derivative is negative on the interval AB, then f does what? Decreases. Inclusive. Now, I will tell you, and we will get to this very, very soon, that the converse of this is, what does converse mean? Okay. Right. Remember where you had if-then statements in geometry, and when you switched the if and the then part, that was the converse? The converse of this is also true. So if f is increasing on AB, we can assume that the derivative is positive. And if f decreases, then we can assume the derivative is negative. Does that make sense?
Yeah.
See where we're going to be going the rest of this chapter? Okay, so right now we're looking at it forwards, but we will look at it backwards. It's true forwards and backwards is what I'm saying. Really, it's, you remember what you called those in geometry?
No, I thought it was
If and only if statements, you could use an if and only if. If you can read it forward and backwards, yeah. Do you?
yeah. And then
So the sign analysis is going to be key here. Okay, so this was the first day's worth of stuff that I gave you, where you were basically doing the same thing as the extreme value theorem, but in this case, I think most of them had endpoints. We had 15 through 28, is that right?
So it seems like just making
Use,
sign.
it is. This is all about sign charts. Sign charts will be your life here through this chapter. I know. It's so exciting. So you had to find, and I'm looking just at number 15 and going that direction. You have to use analytic methods to find the local extrema, the intervals on which the function is increasing and the intervals on which the function is decreasing. I'll do one with you quickly before we move on. I'll just do 15, I guess, because it's the first one. It was f of x equals 5x minus x squared. And so what I'm going to do is I'm going to find the derivative, and it's the same process every time. Find the derivative, set it equal to 0, do a sign chart. Okay, give me one that's harder. Let me do a harder one
I
with
do
you.
have a question real quick. So
Okay.
when you set it equal to 0, that'll give you the count.
Okay, so it'll give you your possible extreme values, your possible maxes and mins, right? Because I can't say for sure that they're maxes and mins, because if my function is always increasing, something like this, I don't have any maxes or mins. Those become stationary points instead of changing.
When you plug stuff in.
Okay, so I'm going to plug stuff in after I find out where the derivative is 0. So the first thing I want to do is find the derivative. This one did not have an interval, so it's unbounded. Okay? So my intervals are going to include infinity here as I named them. So I set this equal to 0, and I solve. Subtract 5, divide by -2. I end up with x equals what? 5/2. So I'm going to do my sign chart. Here's 5/2, bless you. This is a possible max or min. Okay, bless you, knowing what I know about parabolas and quadratics, this should be a what there? A vertex, so it should be it's a parabola going down. It should be a maximum. It should be an absolute maximum. Because it's upside down, that's right. Okay, so what I'm going to do is I'm going to test some points in the derivative, and I am going to try to see what the function itself is doing. Sure. But I'd probably pick 0, since that's to the left, and that's easy to. Oh no, wait. We can do 0. We can do 0 because we're plugging into the function. So it's still positive. You're plugging. This tells me what the derivative is doing. So here I'm plugging into the derivative, and I'm looking at the sign of the derivative will tell me what the function is doing. I think y'all are getting confused on where to plug in when. That's why I keep writing derivative on the bottom and function. So everything on the bottom is telling me the derivative, and then everything up top is telling me function. So for this one, I'm using this equation. Are y'all with me there? So that means that this is increasing on that interval. The function is increasing on that interval. To the derivative. I use 0. If you do 0, so what is the derivative at 0? 5 minus 2 times 0, which is 5, which is positive. And remember, you don't have to work it all out. You just need to do enough where you can get the sign of it. The answer itself is not that important. It's the sign of the answer that's important. Right. Okay, so if you choose 3, you get negative, right? We can all see that. So it goes negative, which means everything on this interval is going negative. It's decreasing. So now if you think about it, if I'm increasing and then I change direction and I start decreasing, it's going to look like that. This has got to be a what? An absolute maximum. You know it's absolute because it's unbounded. So this is telling me that both ends are going down forever and forever because it's unbounded. Correct. If it gave you a point where? If it bounded it, yes. If it bounded it, you would have to check those values. So if it said on the interval -1 to 1, then I would need to check -1 and 1 to see if they were bigger or smaller than if I had 5/2. The function, right. Because the whole thing is analyzing the function, but we use the derivative to do that.
Like you plugged it in.
Say that one more time. Yes. The critical points come from the derivative. And then we plug in the derivative to find the sign.
So you're saying to find whether it's a maximum in the 2 points like that are the boundaries, we plug that into the actual.
If it is bounded, yes.
So if it's bounded.
And that's where we get into MVT because they have boundaries there.
But you plug those into the actual function, not the derivative.
Right. To find the function value, to find out if it's a maximum or a minimum, if there are endpoints, you plug that into the function, not the derivative. The only thing you're plugging into the derivative is to see if you're positive or negative, because that tells me if I'm increasing or decreasing. Y'all okay? Okay. Plug into the function. Okay. So this tells me, because this is an unbounded function, this tells me that f of x is increasing, and you need to be in the habit of writing these this way with all the justification with it, because AP says that this is no longer adequate. Used to, you could just write that and say, okay, it's a maximum, look at my sign chart. They don't let you do that anymore. They want the written justification. So they want to make sure you understand. So f of x is increasing on -infinity to 5/2. Should it be a bracket or should it be a parenthesis? Remember, the derivative is exclusive. The function is inclusive. We're talking about the function now because that's what they asked us to do, is look at the function. So f of x is increasing on this because the derivative is greater than 0 on, and you can say the derivative again, or the interval again, or you can just say on this interval or anything of the sort. Oh, yeah, sorry. Same thing, but now I named the decreasing interval, so now f of x is decreasing on 5/2 to infinity. Why is it decreasing there?
Because the value.
That's exactly right, man. You are learning. You're doing very well today. I'm impressed. That's not all it asked me to name. It also asked me to name the local extrema. So I need to say that there is. Well, you don't have, this is not bounded, so we don't have to worry about it. So what I'm going to say is f of x has a maximum at x equal, make sure you say x equals 5/2, because if you say at 5/2, it sounds like you're referencing the y value. But it has a maximum at x equals 5/2 because the derivative, what else happens? What tells us that it's a max? The signs change. But say what they change from, because the derivative changes from positive to negative at this point. It would be a minimum. That's exactly right. Do you feel a little bit better about this? Okay. Frame break for just a second. First.
I haven't even learned about it.
Or the conditions before. Of course, this is mean value theorem. I do agree with the lady on the video. It's probably one of the favorites tested on AP Cal. For some reason, they love this theorem. But it's not a hard theorem to understand. You do have to understand the prior, you know how they test you on definitions. You know what they do. They'll go back and make sure you understand. If I tell you it's got to be continuous, you better be able to show me that it's continuous and know that if it's not continuous, you can't use it, and they'll do that to you. So here, F must be continuous on AB and differentiable. Remember, the derivative is exclusive. And the reason is, if I have endpoints, I'm talking about a closed interval here, right? So I'm talking about it's not infinite. It's not going on forever. It's between two values. Endpoints are never differentiable because you don't have a limit from the other side. You don't have a derivative from one side, right? You don't have a limit from it, right? So you can't, endpoints are not derivatives, so that's why it's exclusive there. Okay. Here's what it says. Let me give it to you, and let me just talk you through it first, and then I'll give it to you. It says that if you take those two endpoints of that function, whatever, it does not matter what this function looks like. If this is A and this is B, if you find the slope between those 2 points, okay, yeah, they're going to be C in the middle. Yes, there's C in the middle. Yes, you're right. I connect those two, even though this is not part of the graph, and I find the slope of that line. So in other words, I'm finding the average rate of change of the endpoints. A rock, basic slope, yes? Then somewhere between those two endpoints, there is a tangent line that has that same slope. Has to. That is MVT.
Which is the average, right?
Which is the average. So it says, see, this line here, I would say, and remember, it's at least 1 point. That's a secant. Here's the 10. It's parallel because they have the same.
But wouldn't there be two?
Yes, on this one. Can there be more than one? Yes. MVT says at least one.
Okay.
At least one. There could be more.
You said on Friday you're like two.
Yes, so
you're
there could be,
saying that
sure.
The tangent line at the max or min is parallel to the.
Yes. I would say this one has two. If I was doing this problem. Okay.
So otherwise, the derivative at the maximum min is the same.
Okay, this doesn't have to do with the max and min.
Well,
This is only saying the slope of a line that connects the endpoints is the same as at least one tan line somewhere on there. Slope of one tan line somewhere on there. Somewhere there is a tan line that has that same slope. Where? I don't know. But MVT says somewhere in there it's there. Yes, that is parallel to it because it has the same slope. I'm getting all excited. My watch says, great. Okay. Does that make sense? So now let's put it in terms of an equation. If this is f of x, and this is at x equals a, and this is x equals b, then that means this point is a f of a. Do you agree with that? Yeah. F of a means plug a in and get the y value, right? And this point would be b f of b. Now let's say this point was c. How do you find the slope? Derivative, you're exactly right. So the slope here of this tan line is going to be the derivative at this point C. Do you agree? Does that make sense to you? So slope AROC of endpoints equals the slope IROC of at least one tan line. I'm going to say somewhere.
The question be like, where is that?
It could, yes. Okay, so there it is in words. What does it look like in terms of an equation? Well, how do you find the slope between the two endpoints? AROC is change in y. So f of b minus f of a over b minus a. Somewhere on that graph, that's exactly right. That is all MVT says. There is a tan line somewhere that has the same slope as the secant line. Okay, you're looking, it's not necessarily a max. This doesn't have anything to do with the max or min right now. Yeah, I'm sorry. What you mean the other point? This one?
It could also be
Well, and it doesn't, don't think max and min right now, and don't think highs and lows. All I'm thinking about right now are slopes. That's the only thing I want you to think about right now. Let me show you an example of what I'm talking about. They just happen to fall like that. All right, Lizzie keeps saying 9 and 10. Can I do one before 9 and 10 and then do 9 and 10? Okay. No, once you do it. Let's do number 1 first, because it's easy.
What is this homework? Wait, I already did this.
You probably did. So tonight I just want you to make sure you did it right. All right, so it says, state whether or not the function satisfies the hypothesis of the mean value theorem. Well, the hypothesis there is it must be continuous and differentiable on its interval. Is it mean value theorem? Yes, on 0 to 1, it is a parabola. We know that a parabola is both continuous and differentiable at all points in its domain, and in this case, it doesn't matter that it's cut off from 0 to 1. It is still differentiable and continuous. So yes, it does meet those criteria. Part B, if it does, find each value of C in the interval that satisfies the mean value theorem. So in other words, where does this happen?
Oh, actually, I do.
Actually, you do, because this is A and this is B, right? I don't know f prime of C, but I could definitely find f prime of X, right? Y'all are so nasty. Okay, so let's think about this. Here's my parabola at 0, I'm at -1, and you don't have to graph this, I just want to show you. At 1, I'm at 2. I'm just showing you, this is my piece of a parabola that I'm looking at. So what I'm going to do is I'm going to find the slope of the endpoints, right? Are y'all with me there? And I'm going to find out where the derivative equals that. Okay, well, the slope here, I need to know what's f of 0. No, I just did that. What's f of 0? What's f of 1? I just did it. 2. So what I want to know, so AROC, or my slope, is 2 minus -1 over 1 minus 0. Do you agree? On this little piece of a parabola, just on that little piece, somewhere on this piece, there is a tan line with a slope of 3. Where might it be? Well, what? On the other side. Let's find the derivative first. The derivative, so where might 2x plus 2 equal 3? Well, solve it. We set it equal to 3, right? Because I want to know, where does A rock equal I rock? That's essentially what I'm doing. Look at y'all. I'm glad you think so. So look, at x equals 1/2, here's about 1/2. Here's my point. This tan line is the same as the slope of the, and I know my picture is not accurate at all, and I'm really sorry, but that slope is the same. Try to make it look the same, a little closer anyway. But they have the same slope. The slope of the two endpoints connected is equal to the slope of the tan line at x equals 1/2. Does that make sense? And, yes. Does that seem a little bit easier? Okay, let's do number 9. Oh my gosh. Same process here, just worded a little bit differently. I have an interval. And so the first thing I'm asked is, let A equal A f of A. This looks dangerously like the MVT we derived here at the very beginning. And let B equal BF of B. Looks a lot like that picture we drew to start with, right? Write an equation for the secant line, AB, and the tangent line that's parallel to AB. So let's talk about secant first. What does secant mean? Well, secant just is any line going through 2 points on the graph, right? And in this case, I'm going to use the 2 endpoints. So for the secant in all of these, I'm going to use the endpoints because I know that they're setting me up for MVT. So I might as well use those 2 endpoints there. And it says, I think it says through, yeah, through AB. So if this is A and this is B, all I'm doing is writing an equation of the line AB. I need a slope and a point. I did. My slope would be f of b minus f of a over b minus a. And I'm intentionally writing this harder than you. If you're sitting there on your homework, you're not going to be writing this every time. But I want you to see the connection here with MVT. Okay. So, well, I need to know what a and b and f of a and f of b are. Plug them in. This is a and this is b, yes? So f of a would be 1/2 plus 2. 1 over 1/2 is 2. Or f of 2. No, f of 1/2. Sorry. If you plug 1/2 in here, you get 1/2 plus 1 over 1/2, which is 1/2 plus 2. Well, you got to find the slope between these 2 points.
Those are the 2 endpoints. You know the boundaries at the top right, 1/2 is the same as 1.
I'm just plugging the endpoints in to find out what the coordinates of the endpoints are. So this is 5 over 2. We are. So point A is actually 1/2 5 over 2. Do we all agree? If A is 1/2, I plugged in 1/2 and I got 5 over 2. Mm-hmm. Now point B, so B is 2, so what's f of 2? Right. which is a wonderful problem for Rolle's theorem, because the only thing that Rolle's theorem says, oh, they're the same. And that's Rolle's theorem. Rolle's theorem says that if the two y values are the same, your slope is 0. So you must have a tan line with a slope of 0, which means what? What happens at a tan line with a slope of 0? It's a what? It's a max or min. That's Rolle's theorem. It's just an extension of MVT. When I find this, I'm finding the tan line with a slope of 0. I'm finding an extreme value. That's all Rolle's theorem says. If the two y values are the same, you've got a horizontal slope of 0 somewhere.
I feel like what messes up is like the chapter. Try to work
It is, but it's not. I hope this is clearing up for you. All right, so my slope. Remember, this is still secant I'm talking about. I've gone off on tangents many times to tell you about rolls and all. But at the end of the day, this is just the secant. Y's on top. You can have 0 on top. You can't have 0 on the bottom. So I have 5 over 2 minus 5 over 2 over, it doesn't matter because this is 0. This confirms rolls. This is an example problem for rolls. This is saying that because these two values are the same, I'm finding a horizontal tangent is what I'm doing. Yes. So equation of the secant line would be y equals what? 5 over 2. It's a horizontal line. So, well, if I used one of these points, I would have, and it doesn't matter which one, y minus 5 over 2 equals slope times x minus 1/2. If I simplify that down, I'd end up with this equation.
So what would be
Okay, so for your tangent line in the interval, so it says write an equation for a tangent line to f in the interval AB that's parallel to the line segment AB. Well, parallel means what? Parallel, so my slope would be 0. So what's the equation of the line there? There's not much to do. Make what 0? How do I make the slope 0? Where do I find where it's 0? How do I find where? When the derivative is 0, right? Okay, so parallel, so I'm trying to find somewhere where the tan line, which means derivative, you're exactly right. So if f of x is x plus 1 over x, then the derivative is what? One minus x to the negative 2.
Wait, why is that?
I made this x plus x to the negative 1. And then I used power rule. This makes no sense?
No,
MVT or this is not so steeped in algebra. This is steeped a lot more in the calculus of it, which is probably why y'all like it a little better.
So the reason that
Okay,
works
works.
with the exponent is because we move the x to the first. So x to the negative 1 is the same as x to the negative 1.
Yes, that's right. You're exactly right, because I need to find out where this happens because it asked me for an equation. So where is the slope 0? Because that means where is my slope the same as the secant line slope? Well, so what do? If I add x to the negative 2 over, I'm going to have 1 over x squared equals 1. I just added this to both sides to ensure everything stayed positive. I could essentially cross multiply, right? Or multiply both sides by x squared. Yeah. So 1 equals x squared. What are my values here of x? But now but I'm not done. And I'm not done because it asks for the equation of the tan line. I've got the slope and I've got the x value. One of these doesn't apply. Why? So close. Go back to the beginning of the problem. The interval runs from 1/2 to 2, which means the negative is not in that interval, so I'm looking at when x equals 1.
So we found all that for what?
I need to know the y value. No, we're fine. Remember, this is back to what, okay, we're finding the equation of the tan line. So for the equation of the tan line, we need a slope and we need a point. We have the slope. What's the slope?
0.
We had to find the point where the slope is 0. Well, I know the x part of the point where the slope is 0 is 1, but I need that y part because I need an x and a y to write. Plug it back in the original function. Okay, so f of 1, which is 1 plus 1 over 1, which you're right is 2. Now write the equation of the line with a slope 0 through the point 1, 2.
So x minus, or y minus 2 0 parentheses x minus 1.
So it's just y equals tan line. This line, do they have the same slope? Yes, they're both horizontal lines. Horizontal lines all have the same slope. One of them's a secant line and one of them's a tan line. 9 and 10 are fun. I enjoy 9 and 10. I hope you feel a little bit